So that was how we can store the data of the graph structure. Now we are going to talk about the operations of the graph data structures. So operations on the graph structures are, first thing is the traversing. That was so fast, right? I'm going to show you one more time. So there was nodes propagating like this. So that was the traversing. So what you can do is that we can do the breadth per search traversing and depth per search traversing. And another thing that we can do is the shortest path finding. And then another thing that we can do is finding a set of paths to control the whole vertices. We are going to call it minimum spanning tree. So one thing is the traversing problem. Why do we have the traversing problem? Because that in the tree structures, linked list, in case of the linked list, it was very easy to get all the information from in the linked list to get out the information from the linked list. It was easy because we can just follow this reference structure. However, we have every time we have here two different ways to retrieve the information. Means that getting out all the information from the data structure would be our problem as well. So that problem was called traversing problem. And in the 3 week, we talked about that traversing problem. Graph structure has the same problem. Here, when we need to retrieve all the informations, all the vertices, we can take a number of approaches, and that also being called traversing algorithm. And another set of the operation is the sorted, finding out sorted paths. From 1 to 0, and 0 to 2, and 2 to 9. Might be this would be a sorted path, or there might be another way around to do that. How to find that shortest path? That is another problem. And also finally, finding the minimum spanning tree. So let's just consider that these vertices are all kind of residential areas, and we want to put a logistics center at a certain place. What you want to do is having a minimum path length to deliver our logistic supply to every residential area. So we want to cover all the vertices with the minimum cost. In that case, we want to find out minimum spanning tree. And we are going to discuss these operations in turn in the next coming slide sets. Before we start, we are going to recall the tree traversing. Here we can go the level-wise tree traversing like this, or what you can do is the right-hand side, the depth per search wise. So we go to like this, go like this, and go like this, and then come back, and then come to like this, and come to like this, and then come back, and come to like this, and then come back like this, and like this, and that's the end of the search. So this level-wise search, there is a level-wise search, and also there is a depth-wise search like this. Let's try to do the similar things in the with the graph structure. So depth first search actually utilizes stacks or recursions that imitates the stack operations. There is a pre-order traversing, in-order traversing, and post-order traversing. Actually, we can define those pre-order, in-order, post-order on the graph structures. However, in graphs, often only pre-order traversing is being used. So, for example, if we set 5 as our starting node, like the root, so we need to set a certain node as our starting node. And then what we can do is that it's pre-order traversing, so we need to put out 5 first. And then what we have is that it's depth first search, right? So we are going to drill down until we hit the no further the drill down can happen. So we are going to drill down first this direction. So we hit 3 here. We put out 3 first. It's pre-order traversing. And then we have only one way to follow, right? So 2. So we put out 2 here. And then we have only one way to go. We put out 0 here. And then we have only one way to go. We put 1 here. Like this. So what we did was we actually covered this part and up to this point. There is no further way to go because the 3 is already being covered. Means that we have to retract. We are going to retract to 5. And then our next edge is 4. So we visit 4. So 4. Put 4 here. And then we have only one choice. Go to 6. Put 6 here. And then we have only one, and then there is no further choice, so we retract it. And then we have only one choice to go, and that's 7, and we put 7 here. There is only one way to go. We put 9 here. And then there is actually 2 ways to go, but this is being already covered, so there is actually one way to go, and put 8 here. 7, like this. So that is our depth first search result. It's just you can do this with a simple recursion. And the breadth first search is much more fun. In the breadth first search, we are going to utilize the kooc structures. Can you recall how to do the breadth first search with the tree structures? Actually, it's the same. So we are going to start from 5, and we have a queue here. We are going to put queue here. We are going to put 5 in the queue. And then when we put out 5, then we just dequeue the 5, and we put all the children in the queue. So we put 3, 4, 7 in the queue. 5 is being covered, is being printed out, so we put 3, 4, 7 in the queue. And then what happens next is that when we dequeue 3, then it means that we put 3's children 2 in the queue. When we put out 4, we put 6 in the queue. When we put out 7, we put 9 in the queue. So like this. 3, 4, 7 are being covered, and we put 2 here, and 6. We put 2, 6, 9 in the queue. And after that, 2 is being put out here, and 2's child 0 comes here. and after putting our 6 here, there is no further enqueuing process, so 6 is just gone. And when we put 9 here, we can put 2 and 8, but 2 is already being covered, so we just put 8 here. So let's see. So 9, 2, 6, 9 are being covered. And after that, we put 0 here and we put 1 in the queue. And 8 here, we put out 8 here, and then there is no further to enqueue. So that's the end, right? So we put out 0 and 8. And finally, 1 is being here, and then when we dequeue it, 1 being put out, and there is no further to enqueue, and queue is empty, so the traversing ends. So that's how we do the breadth first search. That's being called level order traversing. Actually, having said that, tree is a directed acyclic graph, one type of the directed acyclic graph. In tree, if we consider tree as a graph, you can instantly recognize that there is a direction and there is no cycle in tree. So tree is a directed acyclic graph. Graph may not be a DAG, right? So there is only one thing different between the tree traversing and the graph traversing. You only have to check the repeated visits to avoid falling into cycle. That's the only difference. This is the only difference between tree and the graph traversing.